Welcome back, everyone. Analytical chemistry's internal mechanics can be intimidating, but today we're peeling back the casing of your instrument. In my years of consulting, I've seen two types of scientists: those who view the HPLC as a magical black box and pray for good peaks, and the pros who know that click and pray is a gamble. Today we're going inside the black box to understand the relationship between the hardware's heartbeat and column chemistry. Think of this as driving a manual sports car. You must understand the gears to master the road. Let's open the box. If you've ever tried to drive a manual sports car, you know that power is useless without control. In the lab, a UHPLC system is that sports car. Treating it as a black box is the fastest way to hit a wall. Success often comes down to the sub-microsecond timing of a pump, or a single Silanol group that wasn't properly capped. Hope is not a management plan. To get world-class data, you must understand the heartbeat of the pump and the hidden chemistry under the hood. Today we turn that black box into a glass one. Before we start the engine, let's look at our mission. We have 4 milestones today. First, we'll trace the history of speed, from Mikhail Tsvet's powdered chalk to the insane 1500 bar pressure of modern UHPLC. Second, we'll master the life support system, including degassing and pumps. Third, we'll strategize between RPLC and HILIC for MS success. Finally, I'll share the pro's secret of endcapping. By the end, you'll know exactly which knobs to turn to push your system to its absolute limit. To understand the present, we look at the roots of chromatography, which literally means color writing. In the early 1900s, Mikhail Tsvet used powdered chalk in a glass tube to separate plant pigments. It was slow and driven only by gravity. For decades, speed was limited by particle size. Imagine filtering water through a bucket of golf balls. It's fast, but there's little surface area. Now replace those with fine sand. You get massive surface area for better separation, but it's much harder to push liquid through. The quantum leap came in 2004 with sub-2 micron particles, changing everything. Here is the hardware pipeline, a sequence of modules working in perfect harmony. It starts at the solvent reservoir, followed by the degassing unit to remove the silent killer of LC air bubbles. Next is the pump, the heart of the system, maintaining pulse-free flow at high pressures. Then we have the auto-injector, the column oven, and finally the column itself. Every step is a potential point of failure. If the temperature fluctuates by even half a degree, your retention time, or T sub R, will drift. If the pump pulses, your baseline gets noisy. Let's talk about the vital organs. The most common cause of baseline noise is air. Air dissolves easily in the mobile phase, causing cavitation in the pump and a drifting baseline at the detector. This makes accurate quantification impossible. The degassing unit is your first line of defense. Next, modern pumps use multi-piston designs for pulse-free flow. Consistency is the currency of quantification. If your flow rate fluctuates by even 1%, your T sub R will jump around, and your qualitative analysis goes out the window. Always check your pump's heart rate first. Why do we endure the stress of 1500 bar? It's all about the physics of the pressure gap. Standard HPLC uses 3 to 5 micron particles. It's reliable but limited. Modern UHPLC uses particles smaller than 2 microns. By shrinking the particles, we reduce the diffusion path, resulting in sharper, taller peaks and higher sensitivity. However, smaller particles create massive back pressure. To force liquid through that nanosand, we need pumps that hit 1500 bar. In the black box, pressure is the force that drives your resolution. Once molecules exit the column, they hit the detector to translate chemical behavior into an electrical signal. In our world, the MS is the ultimate eyes of the system. The detector produces a chromatogram, a plot of intensity versus time. We look for a flat baseline and symmetrical peaks. We measure the peak height, or small h, and the peak area, or capital A. As a consultant, I look at the shape of that peak. If your degasser is failing, your baseline will look like a mountain range, hiding the truth of your sample. Now for the most critical decision, the column chemistry. Choosing the wrong weapon is the #1 cause of project failure. Reverse phase, or RPLC, is the dominant king, handling about 80% of lab work. But it has a kryptonite: very polar compounds. If your molecule is a small organic acid or a sugar, it won't even stop to say hello to a C18 column. It just washes away in the void time, or T0. That is when you reach for HILIC. It's an orthogonal specialist that catches what others miss. Why does RPLC dominate? Because it offers the best balance for LCMS. First, it has excellent MS compatibility, using volatile solvents like acetonitrile and methanol. Second, it has broad applicability for drugs, vitamins, and toxins. Finally, it's predictable. The logic is simple. The less polar a compound is, the longer it stays in the column. It's easy to troubleshoot and easy to scale. If you are building a new method, you almost always start here. But what happens when the workhorse can't run the race? When RPLC fails, HILIC saves the day. It solves the polar problem by roughly reversing the elution order of RPLC. Here's the secret. HILIC gives you 10 to 100 times higher MS sensitivity. Why? The mobile phase has high organic content, which lowers surface tension and makes it much easier for the electrospray source to create ions. The mechanism involves the analyte partitioning into a water-enriched layer on the stationary phase. Counterintuitively, in HILIC, water is actually your strongest eluting solvent. Let's go deeper, down to the molecular surface of the beads. Most columns use a silica base bonded with bulky C18 chains. Because of steric hindrance, these fat chains can't cover every spot on the surface. This leaves behind unreacted silanol groups, or SiOH. These silanols are acidic and sticky, acting like an unwanted secondary stationary phase. They grab onto analytes and cause peak tailing, that ugly trailing edge that ruins your resolution. As a pro, you don't just accept tailing, you fix the chemistry with endcapping. Endcapping is the invisible chemistry that separates masters from technicians. Since C18 chains are too big to cover the gaps, we use much smaller organosilanes to cap those exposed SiOH groups. Think of it like sealing cracks in a floor. This creates a uniform, hydrophobic surface and prevents unwanted secondary interactions. The result? Beautiful, symmetrical, Gaussian peaks. When choosing a column, always check if it is densely bonded and end-capped. This is your guarantee of reproducibility and peak quality. We've officially peeked inside the box. You now understand that UHPLC isn't just about high pressure. It's about sub-2 micron particles and 1500 bar precision. You know that degassing units and multi-piston pumps are the vital organs keeping your baseline quiet. You have a strategy: HPLC for most samples and HILIC for polar troublemakers. And finally, you know the secret of endcapping. System configuration is about high-precision control over molecular behavior. When you know how to adjust these knobs, you stop being a passenger and start being the driver. You now have the hardware logic and know how to tune the engine. But in science, we don't just feel that a separation is working, we prove it. How do we quantify if our peak is narrow enough to meet standards? Get your calculators ready. In our next unit, the efficiency math, we will dive into plate theory and the legendary Van Deemter equation to put a number on your mastery. We're going to turn your observations into quantitative proof. I'll see you in the next unit.